Today's lecture is very exciting because we're going to state something that is known as Stokes' theorem. We're going to give an example of it, and then we will prove it. Now, some of you might have seen Stokes' theorem in, let's say, multivariable calculus or vector calculus. There are some colleges that have a 4th semester course in calculus, and they usually mean vector calculus, vector fields, operations on vector fields, integrating vector fields, and that kind of stuff. So that's where you see it. So maybe if you've taken one of those courses, you've probably seen Stokes' theorem. And we're going to, of course, learn, this is going to be a generalized, we're going to do a generalized Stokes' theorem. We just call it Stokes' theorem. You can also say this is the modern version. Yet you can say this is the modern Stokes' theorem. The original Stokes' theorem, it goes back to the middle of the 1800s, and it was inspired by something that was happening in physics, and that's the theorem that George Stokes came up with, and that's the one that you'll learn in a vector calculus class. Because after all, many of the people who take vector calculus are learning physics, and therefore it is suitable to see the classical version of Stokes' theorem. But we're doing topology, and we're learning about manifolds, and we're learning about integration, and we're going to learn the modern version of this. This is not the way George Stokes originally written down the theorem, but as you will see, it is a generalization to higher dimensions. And I should also say that we will illustrate exactly how the modern version of Stokes' theorem includes the classical version that you might have seen before. If you've not seen it, it's not a big deal, but I'm assuming most of you have probably seen it. We're going to show how it includes the classical theorem as a special case. And we will also prove it, something that is generally never done in a vector calculus class. You generally never prove the theorem. Even if you're taking advanced calculus that has proofs in it, if they ever teach you about Stokes' theorem, they often never prove it, and they might try to prove it, but some of the steps are very questionable. Its proof is a little bit suspicious, not exactly up to very rigorous standards. But when we do it, as you will see, we'll prove it in a very nice, rigorous way, and it will generalize the theorems from vector calculus that you possibly have seen before. And we will, of course, illustrate examples of this. Now, there's going to be really 2 versions of this theorem. And it goes back to how you integrate. So there's 2 versions of this theorem. There is Stokes' theorem for chains. And then there's Stokes' theorem for manifolds. As we remarked, there's 2 different theories of integration. Sometimes you integrate forms on manifolds, and sometimes you integrate forms on chains, depending which approach you want to use. We're focused on this one. This is the one that we're going to focus on. This is the one that we're going to state with all of our careful definitions. This is the one we're going to do an example, and that's the one we're going to prove. But then I will also show you this one for the sake of completeness, so you see both of them. Okay, so there's 2 versions here. And I should say that here you need to actually assume that you have an oriented manifold, because you can only integrate on oriented manifolds. If you're integrating over the manifold, it has to be oriented, as we talked about last time, because then it does not matter what chart you pick. But if you're working with chains, then the manifold does not need to be oriented, because you're just integrating over the chain itself. So what we need first is we need to define the boundary operator. Now, you might say that we already know the boundary operator, but let's discuss. So we first need to discuss the boundary operator on chains, which we call del. The reason for this is because we have 2 ways of defining a chain. So let's say that X, this is our manifold. So we can define CK of X. So we can define this as the free group generated by all continuous maps from the k-dimensional geometric simplex into X. This is the way so this is what we use. This is what we use when we do homology. And then we can also define it differently. We can also define it as the free I should have said free abelian group. The free abelian group generated by all smooth maps from the k-dimensional cube into X. And as we said, to be smooth on the k-dimensional cube, all it means is that the function can be extended to an open set that contains this cube in a smooth way. This is what we prefer to use when we're dealing with integration. Because it's easier to integrate over a cube than it is to integrate over a simplex. Now, we use the same notation because we are mathematically mature enough to tell them apart. But if you want to decorate this, you can maybe put a triangle here to indicate you're using a simplex, and here you can use a square to indicate you're using a cube. The difference will lie in, of course, how you define this object. So delta k is equal to, by definition, it would be the set of points in R k plus 1. So you go into one higher dimension, and then you require that xi. So xi here, it just refers to the ith coordinate. This is a vector with k plus 1 components. So that's just the ith coordinate of x. That it's non-negative, and that all of the coordinates. We also have this convention that we start counting from 0 as opposed to counting from 1, and that the sum of the components add up to exactly 1. Okay, so this is what we call this the standard k-dimensional simplex. Now, the k-dimensional cube, ik, this would rather be points in Rk. So here you will notice that it's actually the Euclidean space in which it is sitting matches the same dimension. And here the condition would be that every xi is between 0 and 1. And you can call this the standard k-dimensional cube. Of course, if you have a cube, let's say a two-dimensional cube, you can split it in half, and then you get two simplices out of it. So it takes a little bit of effort to show this. It's not immediate, but when we talked about homology, we defined homology using this approach. The reason for this is because the notation is more convenient to do everything using simplices, especially the way you define the boundary operator that takes you from a k chain to a k-1 chain. Here, the boundary operator, you can do it. It's just a little bit more tedious to write out. And this one was just more convenient to use. It's just a sake of notation. There are some books in topology that actually develop homology, not by doing this, but by using this. So they define the boundary operator on these mappings of the cube, and you kind of form the chain complex, and then from there, you can get homology. You get the same thing in the end. It does require justification, of course, but it's pretty believable that you get the same thing in the end, because you can always split every one of those cubes into simplices. So it's not that, it's not some kind of surprising result in the end that they lead to the same theory of homology. But when you're doing integration, it's much more convenient to integrate over cubes, because if you were to integrate over a simplex, then you would have to set up an iterated integral where the limits on the integrations, they sort of become variable limits, and it's like annoying to integrate and all of that. So this is just a lot more convenient to use when you're doing integration. So today, when we talk about chain complexes, we're going to be specifically talking about this one because we're doing integration, so that's going to be more convenient for us. So what we need is we need to describe the boundary operator. So let's first describe the boundary operator when we're using simplices. So this is a quick review. Boundary operator on simplices. So let's say the boundary operator that takes us from a k-dimensional simplex to a k-1 dimensional simplex. So it's sufficient. You can just assume that your chain is just a single simplex, because in general, a chain will be a formal sum of these, and then the boundary operator is defined linearly. So you only have to define what it does to just a single simplex. So the way we do it is sigma is a mapping from delta k to x. And what we do is we define what is known as the ith. We call this the ith face. So the ith face, the notation is not the best notation because it looks like it's a partial derivative, but we are mathematically mature enough to understand that this is not, we're not differentiating this, we're rather talking about boundary, so we can distinguish, we can keep different symbols in our mind without confusing ourselves. So this is going to be a map from the k minus 1 simplex into x, and the way this is defined is if you have, so in general, you let's say it goes from x0, x1, up to xk, k minus 1. So you start counting from 0, and what it does is you take sigma, you just repeat these vertices exactly how they go, and then you're going to just put in the number 0 into the ith position. This is the ith position. So then you would have xi minus xi all the way up to xk minus 1, like this. You just put it into the ith position. I guess I have to be careful here. Is this supposed to be I minus 1, or is that supposed to be I? I'm just going to say I'm lazy and I do not even want to think about it. So if I'm wrong, then you can fix it. That's not that serious. Yeah, you have to kind of think it over if it's like, what's the correct index? But I'd rather not even think about it. So basically, that's what you do, right? The I just indicates which of the coordinates do you set it equal to. And then when you do that, the ith face is now a function of one fewer variable. You see one fewer variable because one of the variables has been set equal to 0. And then we can therefore define the boundary of sigma. This is the way we define it. It would then be a formal sum because this is a chain, so it's a formal sum of its faces. So it's minus 1 to the I, and you take the ith face of sigma, where I ranges from 0 to k. And when you calculate this, this is what you call the boundary of the simplex. We're not going to explain the motivation for this. That's something we've done before. We're just reviewing this. And now what we want to do is we want to define the boundary operator when we're using cubes instead of simplices. So it's going to be the same setup as before, but as you will see, it's going to be a little bit trickier. So as before, we're just going to assume that sigma is an element of that group, and it's sufficient to define the boundary operator on the single simplex, and then you extend it linearly. And so you're supposed to get something over here. So the boundary of sigma has to end up over there. So how do you do this? Well, here is going to be a little bit more complicated. First of all, instead of having the simplex, you're going to have the k-dimensional. You'll have the k-dimensional cube, like that. And here's what you do. So for I between 1 and n, so here the indices go from 1 to n, not from 0 to n. And the other index, which at the moment might be a little bit confusing, but you will see what it does. And the other one is going from 0 to 1. Now, the intuition for here is that this one is supposed to represent the side of the cube. And this one is supposed to represent, you can say the side, maybe I should call it a face. And this one is supposed to represent front or back. That's the idea. And you're going to define the boundary I comma j of sigma. And this is going to be a mapping on one smaller dimension. And this is the way it works. So when you pick your coordinates from x1 to xk minus 1, what you would do is you would take the original sigma and you would substitute. And so the idea here is you're going to choose the ith coordinate. So you have x1, x2. Then you have the ith coordinate. So this would be xi. So the one that's right before that, that's xi minus 1. And then the ith coordinate, you're going to, now this one, you're going to set either equal to 0 or 1. So you set that equal to j. And then you continue. Like that. So whatever this number is, so whatever that number is in j, this number is 0 or 1. Now, if you find this confusing, keep in mind that this is an interval, and the boundary of the interval are 0 or 1. So the idea here is that you're choosing one of the 2 points on the boundary, either 0 or 1, and then you're just evaluating that point on the boundary face. Then you have a function of one fewer variable. Okay, so that's the way you do it. And then the way you define the boundary operator, you define the boundary of sigma. You then define that to be the sum. This is going to be the ith boundary of the jth face. I'm sorry, this is the ith face, and then you have the front and back. And then here you're going to put the alternating sum, and it's going to be I plus j. So as you can see, the boundary operator is a little bit more complicated than it is with a simplex. And just to show you an idea, let's do it for 2 dimensions. Actually, something funny happens. If you do it for 1 dimension, so if k is equal to 1, then this does not really make sense because this becomes an empty function. This is not a problem when you're working with a simplex, because with the simplex, when you have delta to the 0, that's not an empty set. That's just a point that sits on the real line. So it actually does make sense. That's like another reason why why it's more convenient to use a simplex. But when you're using cubes, there's a special exception that you need to make when k is equal to 0. And in mathematics, we do not like to make special exceptions. So that's why when we use a simplex for homology, we have the same consistent approach in all cases. But here, we'll return back to what happens when k is equal to 1. But let's just talk about what happens when k is equal to 2, let's say. Okay, so here's what happens. So let's say we have sigma from I2, which is, of course, 0, 1 cross 0, 1, mapping into some manifold x. Okay, so the idea here is we're mapping this 2-dimensional cube, and when you map it, you're going to get some kind of curvilinear. So maybe this is some kind of manifold, whatever that is, and you're getting some kind of curvilinear square sitting inside your manifold. That's the idea, right? This is the way we visualize it. That's like the image of it. And the idea here is you move along the boundary using the right-hand rule. So imagine that the face that you see is pointing towards you. So take your right thumb. Okay, so take your right hand. So this is like your right hand, your right thumb. So this is like your right. Let's say this is your thumb. Okay, that's your right thumb. And position it so that it points towards your face, right? So it's pointing towards you. So it's perpendicular to the square, and the thumb is pointing towards you. And now curl your fingers. So as you curl your fingers, you will see you're moving like this around the edges. And you want to be able to indicate that in the picture. Now, whenever you map this to the manifold, there's this question of orientation. How does the normal that it's pointing towards you, how does it point? So let's say, for simplicity, the normal is pointing outside. Okay, so this arrow, which is perpendicular to that surface, in this picture you cannot see it because it's kind of going towards you, right? So it's pointing towards you, and when you map it, this is the side that you see. So now if you use your thumb and you curl your fingers, you're going to notice that you're traveling like this around. And the boundary operator is supposed to give you those 4 paths that go around it. So, but how do you do it? Well, here's the way you do it. You're going to say that the boundary of sigma is going to be, you're going to do 1 comma 0 of sigma. And here the sign is going to be negative because the parity of I of 1 and 0 is -1. And then you do plus, then you have boundary of, so you add these together, right? When you add them together, that would be 1. Then you have the boundary of 1 comma 1 of sigma. Here you add these together, that would be 2. Then you have boundary of 2 comma 0 sigma. This would be 2. And then you have, the last one you have is this one. This would be 3. Okay, so you have to understand that the first one, so let me just break this down again. The I, this is the coordinate. Which coordinate are you picking? And this one is either 0 or 1, coming from the interval. It's the endpoints of the interval. So there's only 2 coordinates for this function. It's a function of 2 variables, so 1 or 2. But what you put for j will always be 0 or 1. So in general, what I should have said over here is I will range from 1 to n, and j will range from 0 to 1. So in total, you will have 2n terms. So you'll have more terms when you're using a simplex. So if you think about this, a 2-dimensional triangle has 3 faces. A 3-dimensional tetrahedron has 4 faces. So an n-dimensional simplex will have n plus 1 faces. But here, an n-dimensional cube will have 2n. You have n here, and you have 2 choices here, so you have 2n faces. So there's more terms here, so it's a little bit more complicated. But other than that, it's kind of similar, and let's actually work this out. So let's work this out. So what is this one? So this one, boundary 1, 0, sigma, this is now a map on a cube of 1 smaller dimension. So in other words, this is just a mapping from the interval into x. And what is it doing? You're just taking sigma, you're taking the first coordinate and you set it equal to 0. And then that becomes your free variable. So if you call this letter s, then that becomes your s. So this is the mapping. So this is the mapping that keeps the first coordinate equal to 0, and it takes the second coordinate and it makes it go from 0 to 1. So in the picture, this is the square, right? This is the square. And in the picture, you're setting the first coordinate, which will be the horizontal coordinate, you set that equal to 0, and then you make it vary from 0 to 1. So you're moving like this, right? So as you keep the 0 and you let s go from 0 to 1, you're tracing out, you're looking at the image, right? You're looking at the image of this edge. But you can see you want to go the other way, right? You want to go the other way when you're using the right-hand rule, so that's why you set it to be -1. And in the picture, it's the one that's going, let's say, like this. So it's visualized, right? So this is now a path in x. That's now a path. With the other one, let's say 1 comma 1, when we write over here 1 comma 1 sigma, that's a mapping from 0, 1. This is a 1-dimensional cube into x. And how is this being defined? Well, here you're taking the first coordinate and you set it equal to 1. So that would be 1 comma, and that's your free variable. So as before, if you call this one s, this is also s. And so in our picture, you're setting the vertical coordinate to be 1, and then you're moving from 0 to 1. So you're moving this way. And now you're moving in the correct orientation with the right-hand rule, and that's the reason why this one is positive. Let's do one more. Let's do this one, the very last one. Let's understand what that one says. So this is 2 comma 1 sigma. This is now a mapping of 1 fewer variable. So this is a 1-dimensional cube into x. And then the idea here is that how is it defined? Well, you take the original mapping sigma, you take the second coordinate, and you set it equal to 1, and then this is your free variable. So if this is s, that would be your s. And in the picture, the horizontal coordinate is equal to 1, and s moves from 0 to 1. So you're moving this way, right? You're moving in that direction, which is in the wrong direction, because you want to move that way. And so the image of that path, it will give you a path with the wrong orientation. And since you want to go the other way, you just arbitrarily change the orientation by putting a minus sign in front of it. And the picture here is you're getting a chain, right? You're getting 4 paths. It's a formal sum of 4 paths, and the signs are chosen to match the orientation that you want when you use the right-hand rule. That's kind of the way it's done. It's very similar to how you do it with a simplex, but it's just defined a little bit differently because we're using cubes. And as I remarked, there is when you do it in, you see, when you do it when k is equal to 1, then you get something that does not exactly make sense. So you have to treat it as a special case. Whereas when you're working with simplices, you do not have to treat a special case. But let's just see what happens if sigma is from I1 into x. Then the boundary, so what would be the boundary of sigma? So you would say the boundary of sigma would be, you would take the sum over all I and j of this. The problem, of course, is you only have one coordinate, right? It's just a single variable. So you would have boundary 1, 0 sigma. That should be with a minus sign. And the other one should be plus boundary 1, 1 sigma. Because there's only one coordinate, whereas the endpoints are 0 or 1. Now, the issue, of course, would be, how is this defined? Well, you would say that, let's say boundary 1, 1, it should be a mapping from the 0 cube into x. And then the question is, what does this even mean? How do you, it's unclear what that means. It's unclear. So rather, what we do is we simply, the way we interpret this is we take the first coordinate and we set it equal to 1. So we just define this to be sigma evaluated at 1 because there's only one coordinate and you're evaluating at 1. And this would be sigma evaluated at 0. And so what we're getting is that then the boundary of sigma is sigma of 1 minus sigma of 0. And this is, of course, this is a formal sum of points in X. So here the idea would be that if this is like your manifold and you have sigma, let's say this is sigma, this is what it does at 0, that is what it does at 1, then the way you interpret the boundary of sigma, this would be sigma of 1, that would be sigma of 0, and then the boundary is then defined to be the formal difference between the 2 points. So you have to somehow treat a special case, you have to define C0 of x. So when you're using these cubes, you then have to define this as a formal sum of points in X, as opposed to mappings. When we're dealing with simplices, you can always interpret them as mappings. But when you're dealing with these cubes, you have to make a special exception for 0. And some people would say that's a bit annoying, that you just have to treat it as a degenerate case. And that's like one of the reasons why, that's like another reason why we're doing homology. We prefer to do it with simplices. But for now, we'll stick to using cubes for the purposes of simpler integration. So that's the way we define it. And now we can get to what Stokes' theorem says. So this is Stokes' theorem. Let X be a manifold. We do not care what dimension it has, but it's a manifold, a smooth manifold, of course. Let omega, so when we integrate, we use differential forms. So let's say we have so we're going to have a form, and this is going to be a form of degree k minus 1. And C is going to be a chain. So of course, you can maybe indicate this as a chain using cubes, but I'll write it like this. This is a smooth chain in X, and this is going to be of dimension k. Now you might find this very confusing because you look at this and you say, but the dimensions do not match. We've said that when you integrate forms, you're supposed to integrate a chain of the same dimension. That is true. However, we're about to do something that will make sense. By the way, what does this mean? So to quickly remind you what this means is, this is just, all you're saying is that omega is a collection of forms where each individual, this is Euclidean forms in every chart that are coherent. Okay, so we just write omega, but omega is really a collection of forms in every chart. And this is just a formal sum of simplices, right? So the C would be, it would be some integer a1 times a simplex plus another integer times a simplex and so on. Here, when I say simplex, I really mean a k-dimensional cube. So that's what C is. And this is what the theorem says. It says that when you integrate the boundary of C, now notice, when you integrate the boundary of C, the boundary, right, the boundary operator applied to a chain will give you a chain of one smaller dimension. And you're integrating it over omega, which now has dimension k minus 1. So the dimensions agree, so this makes sense. So it says that if you integrate a form of degree k minus 1 over the boundary of a k chain, that is the same thing as integrating the exterior derivative of the form. Now the exterior derivative will increase, it will increase the degree over the original chain. That's what it says. So it basically says that you can just take this operator and just move it upstairs. That's essentially, symbolically, that's what you're saying. And maybe I should just explain something here so there's no sense of confusion. What does d omega mean? How do you calculate the exterior derivative of a form that's defined on the manifold? Well, we know how to calculate the exterior derivative of a Euclidean form. So we have Euclidean forms in every chart, and all you're doing is you're just applying the exterior derivative operator in every chart. And then you get a collection, and then you end up getting a collection of K forms in every Euclidean chart. And as you had a question on the homework to justify that this is a coherent collection, so that means that this is indeed a K form defined on your manifold. So that's what the theorem says. Okay, very, very nice. You know, let's even put a little bounding box around it. It's a very nice looking equation, of course. The question is, of course, like, why do we care about this? Right? Like, okay, it looks like a nice equation, but why do we care about this? Actually, some people call this the fundamental theorem of calculus. Some people will tell you that Stokes' theorem, this sophisticated modern version of Stokes' theorem, is really a generalization of the fundamental theorem of calculus. Okay, and what I'm going to quote Spivak. So to quote Spivak, so Spivak has a book called Calculus on Manifolds. So when I teach undergraduate multivariable advanced calculus, this is the book that I use. And to quote Spivak, he calls this theorem A, he calls this a fully developed modern theorem. What does he mean? So he actually means three things. The first thing that he means by this, and this is funny, he says it is trivial. The second thing he says, it is trivial because everything has been rigorously defined. And the third thing is it has deep consequences. So I really like the way Spivak puts it, especially when he calls it trivial, because as I've said many times, that's what modern mathematics does. Modern mathematics, it trivializes a lot of the mathematics that you know. So why does it feel hard? Well, it feels difficult because of the definitions. The definitions are very abstract. They're very general. It's sometimes difficult to see the intuition for what you're doing, as opposed to classical mathematics. Like the kind of mathematics that was done 200 years ago or even 150 years ago, it was much more intuitive to understand what people were trying to say. But a lot of the proofs were difficult to justify. Sometimes it was hard proving something in a rigorous way, and sometimes you would have to use these very ad hoc tricks in order to make something work. But modern mathematics has cleaned up a lot of classical mathematics by making it a lot more general, but the price to pay is everything is now a lot more abstract, and the difficulty lies in the definitions. So here, you have to understand a lot. First of all, you have to understand what a manifold is. That's something that did not exist 200 years ago. You have to understand what a manifold is. That takes work to understand what that is. Then you need to understand what a chain is. This is an algebraic type of an object. It's like a group generated by, it's a group generated by smooth mappings and all of that. You have to understand what this means. Then you have to understand what a differential form is. That's also fairly abstract, right? It's a collection of these differential symbolics that are coherent in all of the charts. And the reason why you want that is because you want something that's invariant under coordinates when you do calculations on the manifold. Then you need to understand the boundary operator, then you need to understand the exterior differential operator, and then finally, you need to understand how you integrate forms on chains. So you need to just understand all of that before you can even write this down, and that's where the difficulty lies. Whereas classical mathematics, when you write classical Stokes theorem, it's a lot easier, much more intuitive. You can kind of explain it in a single lecture. You do not need this long, elaborate build-up to all of these definitions. But as you will see, and this is the part which is kind of funny, that when Spivak calls this a triviality, he really means it. Now, it does take some work to prove. It's not like one line. You have to work it out. But as you will see, as we prove it, there's absolutely nothing clever in the proof. You just carefully apply the definitions, and the proof just immediately presents itself. There's no clever tricks that need to be done in order to justify this. And lastly, and this is the other part, it has deep consequences. And sometimes this is difficult to see. Sometimes it's difficult to see why it is important. Like when you look at something like this, it is by no means obvious why it's the fundamental theorem of calculus. It's also by no means obvious why it generalizes like classical Stokes theorem. So these things are by no means obvious anymore. But that's what we have to do. We're going to try to demystify that, demystify that, so you get to see how it's connected to the fundamental theorem of calculus, and we're also going to show how you get the classical Stokes theorem from vector calculus, and you get many other theorems beyond that, and then you will see the kind of connections it has when we return back to homology, and we talk about cohomology as well. So you're going to see those connections come up. But this is basically what the theorem says, and you should be in the position to actually understand what this is saying. Maybe it's not clear why it is yet, but at least you understand what this theorem is actually saying. And what I want to do next is I want to provide you first with an example of a calculation, so we get to compare both sides, and you see it gives you the same answer. Then I want to show you why some people call it the fundamental theorem of calculus, and then I'm going to show you why some people call it Stokes theorem, even though that's not the way George Stokes originally written it out. And then after that, we can go on and talk about how one would prove that. So that's the plan for the lecture. So now that we have the theorem, we can appreciate it one more time. In fact, let's remove all of that. Let's just keep the theorem on the screen. This is sort of the main theorem, and we can even like zoom in so you get to see it even better. So that's the theorem, and that's what we're going to do in our example. We're going to do an example that's going to illustrate Stokes theorem. So first we need a manifold to use. So in this example, let our manifold X be the plane, the two-dimensional plane, removed the origin. Okay, and this is a smooth manifold. And you can use a single chart. With a single chart. So the atlas here, so the reason why this is a manifold is you just use this as your open set, and then you can map it homeomorphically into X. So your mapping, maybe I should call this phi, consists of just phi, where phi is the map from this open set into X. And this is just the identity map. It's kind of silly, but I'm just doing it to reinforce the definition of what a manifold is. You might be bothered by this. You might say, is it not the case that this should be R2? Because that's the way we set everything up. That is true, that in a lot of the times in the definitions in general, we just assume it's Rn, where n is the dimension of the manifold, because it's just more convenient. But you did have a problem on the homework that allows more flexibility, that when you have charts, they do not necessarily have to go from Rn. They can go from U, where U, like U lambda, this is just an open set in Rn, where n is the dimension of the manifold. You can have a little bit more flexibility. Sometimes that's convenient. So here we're going to use our open set will just be the punctured plane. And this is the identity map because X is already that. So this is a homeomorphism. Its image completely exhausts the entire space. So therefore X is a smooth manifold. So we have a smooth manifold with the identity chart. The next thing that we need when we use Stokes' theorem is we need a form. So we will construct a one form that will be globally defined on all of X. So what is a one form? So in general, we say that omega is a collection of forms in every chart, right? So lambda is the indexing set for the chart. In this case, you only have a single chart. And so a form would just be a form defined in this Euclidean open set. Okay, so here, so in this example, omega would simply be a one form defined on the Euclidean chart. Here it's a bit confusing because the manifold and the Euclidean chart are the same since you're using the identity map. But this is why I'm calling it X, so you can sort of distinguish between them. But because you only have one chart, you have to define a form just on this. I mean, it's the same thing as saying defined on X, but I want to specifically write it like this because in general, X is some abstract space. So this will be defined on the Euclidean open set. Okay, so for example, in this example, I'm going to use the following form here. So let's say it's going to be y divided by the square root of x squared plus y squared, where these are the projection functions, right? This is a two-dimensional open set, so you can talk about coordinates. So these are the projection functions. So the projection functions are going to be x and y. So x simply represents, so if I pick a point on this set, x represents the first coordinate, y represents the second coordinate. So these are the projection functions. So omega would be this function, and then I have to use, I want a one form, so I have to use differentials in terms of those projection functions. So let's say, to make up the example, let's say it's just dx. So that's going to be our form. And whatever this is going to be a one form defined. Now, I'm not going to write x, even though that's technically correct. I just want to keep on repeating this again, that when the way we're doing it, the forms are not defined on x. The forms are rather defined on the Euclidean charts. I know that here they're exactly the same thing, but I do not want to write this because in general we always go back to the chart. So this would be on R2, take away 0, 0 like this. And you can see this is defined on this open set because the origin is missing, so there's no, and this is a smooth function, right? Smooth function. This is just a symbolic. So that's our form. And now we need a chain. Okay, so then we need a two chain in X. So we're going to pick a two chain that's going to be contained in X. So why are we picking a two chain? So the reason for this is just to write Stokes' theorem here in the corner. We're going to show that if you integrate over the boundary of the chain of omega, that's the same thing as the integral over the exterior derivative of omega over the chain. So if it's a two chain, its boundary would be a one chain, and then the dimensions match. So this is what we're going to be verifying. That's what the example is going to show, that you're going to get the same calculation if you do it two different ways. So we need a two chain. So now this is going to be abusive. This is going to be intuitive, but then we'll make it a little bit more precise. So the abusive way to say it, technically this is not correct. We're going to pick C will be the annulus of radius 1 and 2. So as a picture, X is the punctured, this is the punctured plane. So maybe I should make like this is a hole. That's a puncture. That's what X is. And the chain, this is a two chain, so a two-dimensional chain. You would have a circle going like this. You will have a circle going like that. And then you will make the annulus that goes around the hole. So this is going to be C. Now, the reason why this is abusive is because you have to understand that C is not a subset of X. It is rather a mapping from a two-dimensional square, two-dimensional cube into X. Okay, so that's why it's abusive. We often draw the image, but we have to work with a mapping. So we have to find a way to parametrize this. And actually, the way you parametrize this might give you a different answer. Because if you, let's say, do the orientation in a different way, you might get a different answer. Or, for instance, maybe if you like wind around twice, you might get double the answer. So this is why I say this is abusive. This is not well defined. It's not, you're always going to get a different answer depending on how you choose to parametrize this. But I'm just writing this down to give you a picture in mind. So formally, this is more formally. C is going to be the following simplex. So this is just a single mapping from the two-dimensional square into X. So our chain will consist of just a single mapping. In general, it's a formal sum of lots of these mappings, but in this case, we'll keep it simple. And the way you can do this is by using polar coordinates. So we're going to define sigma, and this is going to be a map from 0, 1 cross 0, 1. This is going to be mapped into X. And because you have two coordinates here, you're going to give them names. I'm not going to call them X and Y because I'm already calling them X because I already used that. So you can call this one, you can call maybe the first one R, and you can call the second one theta, for instance. And this is going to be the mapping that R comma theta. So you basically want to say X comma Y, basically, right? You're basically saying what X and Y become in this manifold. So with polar coordinates, you would typically write R cosine theta and R sine theta. This is probably the way you've seen it done in calculus. But because we're keeping theta to be between 0 and 1, we're doing everything on the unit interval. We're just going to make a small little adjustment. This is going to be 2 pi theta. This is going to be 2 pi theta like this. And then here, R, because we want the radius to go from 1 to 2, we just make a small little adjustment. And we're just going to write this as R plus 1, R plus 1. Okay? And now we have a smooth function. This is a smooth function because it could be extended, right? You can easily extend this on all of R2. You're just restricting it to the square, but this function extends smoothly to all of R2. So this is a smooth mapping into X, and this is the rule for the mapping. So that's our chain. It's just a single mapping. Now, the question you can ask, and this is like an interesting question to keep in mind, an interesting question to think about, and we will answer it later. And actually, it is so. It's not actually important because the formula for Stokes' theorem will automatically do it for us. But it's just interesting to think about how is it oriented? How is this annulus oriented? Now, what do we mean by oriented? So what we mean by oriented is actually very simple. We're mapping a two-dimensional square, right, two-dimensional cube into our space. So the picture that you want to have in mind is this is the two-dimensional square, and sigma is mapping it into X. So when you map it, like the idea here is you're going to take like two of these edges and you sort of glue them together to make these circles out of them. But the question is that the side that you see, right, this is the side, this is the normal perpendicular to the square. That's the side that you see. When you map it over here, is this the side that you still continue to see, or does it flip over and does it go the other way? We'll answer the question while we do the calculation. It's actually not going to be important for us because the formula for Stokes' theorem will automatically do it for us. But you have to be very careful here because if we, let's say, came up with sigma theta comma r, and we kind of interchange the roles of theta and r the other way around, then we would actually get something that would flip that square over the other way. So it's always a question of orientation. Sometimes it's nice to think about it, but it's not actually going to be important for us to solve the question. So this is our mapping. So we have constructed a one form on our manifold, and we have constructed a two chain in our manifold. So the next thing that we need to do is we need to calculate we need to calculate the boundary of that chain. I'm sorry, before we calculate the boundary of the chain, let's calculate the exterior derivative of omega. So let us compute d omega. In this case, so in general, what you would do is that you go back to omega. Omega is a collection of Euclidean forms, and you would take the exterior derivative of every one of those Euclidean forms, and then you get a new coherent family where all of the forms have one higher degree. And that's the way you calculate the exterior derivative of every of the form. In this case, because you only have a single chart, right? It's an atlas of a single chart, and this is the form that you're using that's defined on that chart. You would simply calculate the exterior derivative of, you only have one thing to work with, and it's just that. So you're going to go ahead and calculate that. So here's what happens when we compute it. So we get that. So actually, let's write. So our form is a function times dx, where the function, the coefficient function, it's a smooth function, and it's what we've written up here. It's that function over there. So it's y squared of x squared plus y squared. That's what this is. So then the exterior derivative of omega would be equal to, so the way you calculate the exterior derivative of a form, you apply the differential operator to the coefficient function, and then you wedge it with all of the differentials. So here there's only one differential. So this is a differential, whereas this is the exterior derivative applied to a function. So you have to differentiate this. So the way you do it is, by definition, you have to do df dx. You have to differentiate it with respect to x. Then you write down the differential plus df dy. Then you write down the differential, and then you wedge it with dx. Now, as you can see, this one will go away because dx wedged with dx, our formal rule in the differential form algebra is that it becomes 0. And so we only have to differentiate this with respect to y and get something out of it. Now, you just have to do this either by hand. I did it on Wolfram ahead of time. You just have to differentiate that with respect to y. And if you do that, you will get, I mean, I'm not going to write it out. I mean, we all know how to do that. You will get that this is negative. When you fully simplify, it's negative x squared. And let me just check what it was. It was x squared plus y squared to the 3/2. And it's dx wedge dy. And if the negative sign bothers you, you can absorb the negative sign and switch these around and make it be dy dx if you really want to do that. And whatever this is now a 2 form defined on X. So again, because X, our manifold, consists of just a single chart, it is sufficient to only do this calculation in that one chart. And that chart is just the punctured plane chart. So we're getting a form, a 2 form, that is defined, whose coefficient functions are defined on that open set, open Euclidean set. So that's what we get for d omega. So what we're going to do next is let us compute the integral of d omega over the chain. So how do we do this? Well, in this case, the chain consists of just a single mapping. So we go back to the definitions of how this works. So in general, if you're mapping a 2-dimensional square into your manifold, okay, and well, let's do it like this. So let's say, I'll draw a picture down here. So let's say we're mapping our 2-dimensional square into our manifold. I know our manifold does not look like that, but I'm just being more general here. And let's say this is what we're calling sigma, and sigma gives us a curvilinear square on our manifold. Let's assume that this is sitting inside a chart. So there's an R2 over here. And more generally, I mean, you couldn't just say it's just in general. It could be an open set of R2 that's being mapped by phi, where phi is so this is the homeomorphism onto that open set. Okay, so you have this, and then if you do this composition, sigma composed with phi, then right, you have this, and you have a form. So a differential form on the manifold would be described by forms on each of these charts. So you have a form. Maybe I should not call it omega. Maybe I'll call it eta. So in this case, eta is equal to d omega. So you have a form defined on this one, and the way you integrate is you pull it back. So basically what I'm saying is, like, pretend that this was the integral over eta. Then what you would do is you would pull everything back to I2. You will take your form and you will pull it back using that composition. I should have written over here, sorry about that, I should have written phi inverse. So phi inverse composed sigma. You pull everything back. So you pull back, this is a two form that's being pulled back to I2. And whatever that is, this is now a 2 form on the square, and then you just integrate the function, right? It's because it's a 2 form on a 2-dimensional region, it would just be some function followed by all of the differentials. So you just integrate the function that you get. So that's how you do it in general. So in our particular case, our form eta is, so we're using Stokes' theorem. So our form is what we're calling d omega. So what we would do is we would say you pull everything back to I2, and then our function phi, right? This is just the identity map, right? That's our identity map. So that's just it. So it's the inverse, right? It's the inverse of the identity map because we have the identity chart. So it's not doing anything. And then sigma, that's just, I mean, that would just be sigma. So you just do sigma, you pull back sigma, and you pull back d omega. So that's what you're pulling everything back to sigma. Now, how do you do this calculation? Well, let's look back. So this d omega, so in our picture, this is R2. Take away the origin. And our form, well, we calculated it. It's this. Our form is negative x squared over x squared plus y squared to the 3 over 2 dx wedge dy. That's our form. And sigma, well, sigma going to there and then going back here with the identity map, this is just a map that we also written out. This is the mapping. So sigma, so the mapping going from here, so if we call the coordinates here r and theta as the projection functions for I2, right? That's the way we've decided to call the coordinates here. Then this mapping is the mapping. Maybe it would be better to use a different letter. Maybe I'll call it like G. So that, I mean, technically they're the same thing, but maybe it makes it better to distinguish it. We call that G. Then this mapping, G, what does it do? So G takes r and theta, and it maps it to r plus 1 cosine theta and r plus 1 sine theta. So you're doing substitution. So basically you're saying that the x coordinate, that's the x coordinate, that's the projection function on this chart. It would be this. So you're essentially setting x to be equal to r plus 1 cosine theta, and you're setting y to be r plus 1 sine theta. So how do you then do the pullback? So to do the pullback, apply to this form, what you would do is you would replace x and y. So you're going to replace x. So x gets replaced by all of this. So that will be r plus 1 squared cosine squared theta divided by x squared plus y squared. So in polar coordinates, that will be r plus 1 squared raised to the 3 over 2. And then you have dx. So you have to differentiate. You have to find. So you take the dx here is referring to the first component. So g has 2 components. So it's the first component of g. And then you calculate so this is your function of 2 variables, and you calculate the exterior derivative of that. So that would be basically dx dr plus dx d theta wedged with dy dr plus dy d theta. And now we go ahead and do the calculation, so you should get, so I think I did this ahead of time. So this is what you would get if you do it. So well, actually, I realized that, yeah, I made a mistake here. This is supposed to be cosine 2 pi theta, 2 pi theta. So this is equal to, this is boring computation. I would suggest that you try to do it yourself. So if you do this, so I did it ahead of time, you will end up with negative 2 pi. If you're wondering where the 2 pi comes from, this is simply coming from the fact that when you differentiate cosine using the chain rule, you pick up a factor of 2 pi. So you get negative 2 pi, and you're going to be left with cosine squared 2 pi theta, and then you would be left with, let's see what I did over there. You would be left with dr wedge d theta. That's what you're left with. You will notice I'm keeping it as dr wedge d theta and not d theta wedge dr, because r plays the role of the first projection function, and this plays the role of the second projection function. So that's the way we've decided to do our mapping, where this one goes first. So this is what you end up getting. You can maybe kind of see that, because you see you have cosine squared, right? You see cosine squared. This is technically supposed to be 2 pi theta. Then you have r squared, r plus 1 squared. Then you have r plus 1 cubed, right? This will be cubed. And if you do this calculation, you will pick up another factor of r plus 1, and they will cancel each other away. So you can kind of see that when you do the wedges, you're going to skip these two. These will cancel because they're being repeated. So you just have to go through the calculation carefully. It's a little bit boring, but you can try doing it. So this is what you end up getting when you do that. So in order to therefore do this integral, you would have that this is the integral over I2. It's negative 2 pi cosine squared 2 pi theta, and you have dr wedge d theta. But this really does not do anything when you do the integration. You now have a function of two variables in terms of r and theta that you're integrating over the square. So you go ahead and you integrate this. So you do an iterated integral. So you just integrate, let's say, from 0 to 1, negative 2 pi cosine squared 2 pi theta. Which one do you want to do first? It does not matter. And then you do another iterated integral. And again, this is a boring computation. I actually did all of these computations using Wolfram Alpha. And if you do this and you work it out, then you will get that it's equal to, in the end, you get that it's equal to pi. That's what you end up getting. So basically, well, I don't want to say anything else. I mean, this is what you end up getting. So when you do that, that's what you will end up with. Okay, so, well, actually, I'm not sure. Maybe you're supposed to get negative pi, because this is, well, it's either pi or negative pi. I mean, you can try doing this yourself. So this calculates 1/2 of Stokes' theorem. You see, we calculated the integral of d omega over the chain. Over the chain. Now we have to do the calculation the other way around, and we have to calculate the integral of the boundary of the chain of omega itself. So let's actually, I'm going to remove this part down here, because we just did the calculation and we're getting either pi or negative pi, whichever one it is. Looks like it should probably be positive pi, but you can check that yourself. So I'm going to remove all of this, so you sort of keep that answer in mind. And now we're going to redo the calculation all over again, but this time we're going to calculate the boundary of the chain first. And then you'll see how this works. So let's just remove this. So we computed d omega. So now what we'll do is, the idea is we want to say that this is equal to the integral of the boundary of the chain of omega. We already know what omega is, so we have to find the boundary of the chain. So now, instead of calculating d omega, we're going to calculate the boundary of our chain. So let's remove all of this, and let's do the calculation again. This is the second half of the calculation. So let us compute the boundary of our chain. Okay, so since our chain consists of just a single mapping, we can then say, so hence, the boundary of the chain, that would be the boundary of sigma. And the way we find the boundary of sigma, this is the way we're going to do it. We're going to find boundary 1, 0 of simplex. This is going to be negative sign. Then will be plus boundary 1, 1 of sigma. Then we would have minus boundary 2, 0 of sigma. That should be plus, and minus boundary 2, 1 of sigma. That's what it is. That's the definition of the boundary operator. This is the way we define the boundary operator. Now let's calculate what these are. Okay, so keep in mind, so recall. Well, actually, we have it written up here. Right, we have it written all the way up here. So let's calculate this. So boundary 1, 0 of sigma, this is going to be a function of a single variable. Maybe we'll call that variable t for time, because after all, this is a two-dimensional square, and the boundary should consist of 4 paths that go around it. So we'll call t for time as you move along the path. So the way you get this function, so all of these, so maybe we can say that, just to not forget, that every single one of these will be a mapping from the one-dimensional cube into our manifold X. So we're just calling this variable time. Okay, so what we do here is we would therefore say that boundary 1, 0 sigma of t, the way we do that is we just take sigma, we're going to look at the first coordinate, we set it equal to 0, and the other coordinate is free, and we call it t. So we're setting r to be 0 and theta to be t. So we end up getting cosine 2 pi t sine 2 pi t, like that. If we do it for the other one, so let's do it for 2, 0. Boundary 2, 0 sigma of t, that would be sigma. We're setting, so actually, no, I did not want to do that. I want to do it not with that one. I want to set the first coordinate equal to 1. That's what I want, the first coordinate equal to 1. So that would be sigma 1 comma t. So here you're setting r to be equal to 1. So that would be 2. So we have 2 cosine 2 pi t, 2 sine 2 pi t. We get that. So the image of this is the circle. I mean, you can already kind of see what this is. This is the parametrization for the unit circle as you go around one time, and this is counterclockwise, and this is counterclockwise going around the outer circle with radius 2. The other two are going to be a little bit more interesting. So the other one, this is going to be sigma. So which one are we missing? So we're missing 2 comma, let's say 2 comma 0. So here we set the second coordinate to be 0. And now if you set the second coordinate to be 0, sine goes away, and this is just cosine of 0, which is 1, and we end up with just t plus 1 comma 0. And this one, this would be sigma 2 comma 1 sigma. This is the last remaining one. So this is going to be sigma t comma 1. But that's actually going to be the exact same thing because that's cosine of 2 pi and sine of 2 pi. So that would be t comma 1 comma 0. So what that actually shows you is that this one and this one will cancel each other away. It's the exact same map. So the reason why they cancel each other away is not because you add them component by component. These are formal sums. It's the exact same. It's the exact same function. It's the same identical function that's being repeated twice in the list with a negative sign. So you have 2, 0 and you have 2, 1, and these are going to cancel each other away. And if you think about it, it should in a way make sense, because let's go around the boundary of this square. As you use the right-hand rule to go around the boundary, the outside, basically two of these edges. So the idea here, as you can see, is, and this is how we're going to determine the orientation, even though we said over here the orientation is actually not, it's not important to visualize it because when you use the formula, it's going to automatically do it for you. But it's just nice to see what's going on, that this one is positive and this is the one that goes around the outside of the outside. And the one that's negative, this one over here, the idea here is this one, instead of goes in the opposite one. So the way we have it written over here, this is going counterclockwise, but when you draw it, you're going to draw it with the opposite orientation. So this is the one that goes clockwise around like this. And therefore, this should give you an idea of how this is oriented. It means that the normal should be pointing towards you, because this is consistent by keeping. So if you were to keep your thumb pointing towards you and you kind of curl your fingers, you will notice that this is the way that you go around as you do it. So if you're wondering what happened with the other two, like what happens with these two, well, they become the same. It's basically what you're doing is you're taking, maybe to make it a little bit more explicit, it's basically something like you have one going like this, you have another one going in the opposite way, and they're canceling each other away. Then this is the one that goes around like that, clockwise. So no, that's counterclockwise. This is the one that goes around like this, and the one on the outside is the one that goes counterclockwise. So they're basically two of these, they come together, and it's the exact same path, just in opposite directions, and that's why you're just left with two circles. So the boundary this is a one chain, and it consists of two circles. One of them goes clockwise, one of them goes counterclockwise. So you have to calculate what these are. So maybe for simplicity, what I'll do is I'll call this one O of t for outside circle, and I'll call this I of t. I know the notation gets confused that this is the interval from 0 to 1, but whatever, we'll be able to tell them apart. So we have these two functions. Maybe how about like this? Maybe we'll call this out t, and we'll call this in t, the outside circle and the inside circle. So hence, the boundary of C is out minus in. So it's a formal sum of these two mappings, and you visualize these mappings as paths, and that's what the boundary of C is. And now we're going to calculate, so thus, we have to calculate the boundary of C of omega. So that would be, because you integrate linearly over chains, this is going to be the integral of out of, I meant to say omega. Omega, this is omega minus integral in of omega. So you have to calculate what those are to get your answer. And so let's do one of them. Let's do the one that's on the outside to see what we get for this one. So let's do the one on the outside. So we're calculating an integral over a chain. So this is a path now. So we have a mapping. I mean, just to go back to this again, when you have a manifold in general, and you're mapping an interval to a manifold, and you get a one chain on the manifold, if it happens to be contained in a single chart, which in this case it is, you map that chart using phi, then you have a mapping over here that you're calling, so you're calling that mapping out, right? That's the name of that function, out, the outside circle function. And you have a form over here, omega, and you pull the form back. So you have this composition, call it something, let's call it G again. And you pull it back using omega, right? But if you work out what this is, so the name of the variable here is t, the time variable. And here we have the coordinates here are x and y. And the mapping that goes from here to here is, well, let's look at the formula, right? I mean, this is the out. So this is what you're setting for x, and that's what you're setting. This is what you're setting for x, that's what you're setting for y. So the way you will get this one, it would be the integral from 0 to 1. You map it, you pull it back to the interval, and then you're going to do out star applied, well, technically G star apply to omega, and that would be the integral from 0 to 1. It will be written in terms of dt, because that's the name of the variable. But then to figure this out, you have to just recall that omega was the form. So what form was that? Let me just go back. So that was y over the square root of x squared plus y squared dx. So that was the form that we were using. And what we're doing here is we're substituting. So this is x and y. So x is going to be substituted by, so the function out, this is what is x and that's what was y. So x becomes cosine 2 pi t. This is sine 2 pi t. So x squared plus y squared, that would be 1. That would go away. I messed this up. I called this out and I called that in. So I meant to say that, well, whatever. It's written correct over here, but this should be 2, right? There should be a 2 over here and a 2 over there. So x squared plus y squared, that would be the radius. So omega in this case, you will end up getting y will get replaced by 2 sine 2 pi t divided by the radius, which in this case is 2, and then dx, when you differentiate this, you would get 2, that you will get, you're differentiating cosine, so that's negative 2 sine 2 pi t, and then you have an additional factor of 2 pi dt. So you get all of this mess right over here. So what are you integrating? So you're going to integrate from 0 to 1. When you simplify this, the 2's cancel. There's like a negative 4 pi. Is that what we're getting? Looks like we're getting a negative 4 pi. And we have sine squared 2 pi t dt. So that's what you should get when you do that. And if you do this on Wolfram, if you ask Wolfram to calculate that in, you can use the half angle identity, but who wants to do that? So you just do that and you end up getting that this is negative 2 pi. That's what you get for that one. It's half of it, it's negative 2 pi. So for this one, if you do this one, this is negative 2 pi. And if you do this one, I leave it up to you to check this yourself. If you do that one, you get negative pi. So you get negative 2 pi, negative pi. And so the answer will calculate to be negative pi, which is consistent with the other answer, though it seems I made a mistake. I said it probably is a positive sign. Looks like it should be a negative sign. So that's the way you do these calculations. So of course, I kind of show you the main ideas that lead to the calculation, but if you are, of course, highly recommended to sort of pause these videos and try doing the calculations yourself. And when I say by yourself, I'm not actually saying do like the quotient rule and all that stuff. You can put it on Mathematica so it does it for you, but at least that you can verify every single step along the way. And the point of this computation is to illustrate for you Stokes' theorem, that when you integrate, right, so when you integrate like this, so basically integral of the boundary of the chain is the same thing as this, right? That's what we've shown. This one calculates to be negative pi. That one calculates to be negative pi. And this illustrates in an example of how both computations are done and how they both end up giving you the same answer. Okay, so that was the example. The next question that naturally comes up is, if we're calling it Stokes' theorem, then what is the connection to classical Stokes' theorem? So that's what we're going to talk about next. The next thing to discuss is what is the relation to the classical Stokes' theorem. So how is this, let's say, modern theorem related to the classical theorem? So the classical theorem is a theorem in vector calculus, whereas the modern theorem uses differential forms. If you are familiar with vector calculus, if you've studied it before, and you might have thought to yourself, how does one generalize it to higher dimensions, because you usually just work in 3 dimensions, then differential forms provide the way you would do that. But let's go over the classical theorem. So in vector calculus, we work with something called vector fields. vector fields. You can say it's just a vector valued function as opposed to a scalar valued function. So how does this work? Well, here's the way that this works. You let U be some open set in R3. So vector calculus, you primarily work in space, three-dimensional space. And F is a vector field defined on U. So what does this mean? It just means that F is a mapping, so it's defined on U. But instead of giving you a scalar, instead of returning back to you a number, it returns to you a vector. So the way you want to think of this is you want to think of the domain as representing points in space, and you think of the codomain as representing vectors in space. So the idea here would be is that if you have some kind of, let's say, region, three-dimensional region, so this is U. Maybe I should draw a little bit better. So this is like a three-dimensional region, U. Then for every point within that region, you can assign a vector. So you give me a point over here. That's a point. That's a point inside U. But when you evaluate the vector field at the point, so when you do F evaluated at the point P, you get a vector. And then the way you represent that is at the point, you will simply draw the vector that points in that particular direction. So you would draw some kind of vector that points at that point, and then the vector at a different point. So you kind of do it at every single point. And that's the way you visualize what's going on. Now in applications, this could mean something like this is some kind of body, and at every point inside the body, you have a force vector that's being applied. This can be also a velocity vector or fluid dynamics, whatever it is. So there's all sorts of uses that one does with this in physics, but mathematically, formally speaking, it is a mapping from some open set into R3. This is what we call a vector valued function. And we think of the domain as representing points and the codomain as representing vectors, but formally it's just a mapping of this type. We usually put the assumptions, so we often assume, we will assume that F is smooth. So what do we mean by smooth over here? It just means that because it is a mapping from an open set in R3 to R3, it would just mean that the component functions of F happen to be smooth functions. So that would mean that if you were to take F and you were to write it into component functions, so you were to write it as, let's say, F1, F2, and F3, these are the component functions that make it up. I know that sometimes people in physics, the way they would write it is they would write F1 and they would put I, and they put like a hat on it, but people in physics have often very strange notation. It looks pretty awful, I think, when they do something like that. But I think it's just nicer to just write it like this. It's just three separate functions. They all happen to be smooth. The partial derivatives all exist. Often you do not need it to be smooth. You just need that the partial derivatives exist and they form continuous functions. But we're not going to try to be as general as possible. Smoothness is enough for us. So this is what we could call a smooth vector field. And what you do in vector calculus is you do the calculus of vector fields. You can talk about different ways you can differentiate a vector field, different ways you can integrate a vector field. So this is what we'll talk about right now. So say F U into R3 is a vector field, is a smooth vector field. There is a notion of what we call a line integral, and also something called a surface integral. And it has all sorts of uses in physics. But the idea here would be is you have your three-dimensional body on which the vector field is defined, and the line integral is you would have some kind of curve, C, inside the region, and then you can talk about integrating the vector field along the curve. Now, I should just say that physicists do not distinguish between a set and the mapping. They treat them as sort of the same thing. So when they integrate over C, they always draw the image of the path. They're not thinking about a mapping of a path. We're being a little bit more careful here. We understand that when you integrate over a chain, you're technically using a mapping and not the image. But people in physics do not really care about that. So they talk about integrating f over this curve. And intuitively, what this is supposed to represent is at every single point on that curve, because you have a vector field, you have a vector at every single one of those points. And you can add up all of the vectors. So you can talk about the sum of the forces that occurs as you move along the curve, right? That's the way you can interpret it. This can be interpreted as the sum of all the forces, right? The sum of all the forces along a curve. And in a similar way, one also talks about this thing called the surface integral. Now, physicists, they would write this surface integral using two integration symbols. Oh, I should say one more thing. Sometimes, because physicists like to use funny notation, sometimes they would put something like dot dx, and then they put a hat, maybe a hat here. Maybe they put like they like to just use extra symbols out of nowhere. But basically, if you just ignore the distractions because they do not really do anything for you, if you just basically write down what you're doing, you're just integrating a vector field along a curve. That's the way I'm going to write it. Physicists might have like 10 extra symbols that go after it that do not do anything for you, but this is basically what you're doing. And then when you can also talk about the integral of a surface integral, and they write it with two integrals. Now, we as mathematicians, we only write a single integral, and we understand from context what we're doing. But to be consistent with the notation, they write two integrals. Then you say you're integrating over a surface, and then here you have f, right? You have f again, and here the picture would be very similar. That what this would mean is this is like your body again. This is your three-dimensional body. And then here you would have like a piece of a surface, like let's say a curvilinear surface S. And the interpretation is exactly the same, that at every point on the surface, you're drawing a vector, and then you're adding up all of those vectors on that surface. And the question here comes down is, how do you calculate? So the question is, this is what you'll learn in vector calculus. So in vector calculus, you'll learn how to compute these quantities. And then you see the applications of that probably in like a physics class or an engineering class. But in a vector calculus class, you just learn how to compute it. So how does one compute it? So let's talk about how you compute line integrals, and then we'll talk about how you compute surface integrals. And again, sometimes people put extra decorations at the end. They put like dot ds or whatever letters they like to put in the end. Not that they really do anything, but this is basically what you're computing. So let's talk about how you calculate a line integral. So what you do is to compute the integral around a curve, you parametrize the curve. So the curve can be described as it's x of t, y of t, z of t, right? That the x, y, z coordinates are functions of time, where time, you can assume it goes from 0 to 1. This is basically what you do when you have a chain. So if you have a curve C, now if you have a complicated curve that kind of maybe goes like this or whatever, then you can break it up into pieces, and then you would integrate over the entire chain by integrating over pieces. But a single piece, this is very similar to what we're doing. You're decomposing it as a sum. But if you have a simple chain that can be described with a single parametrization, then you would find the function. This is, you're basically mapping the interval, right? You're just mapping the interval. You're mapping the interval into this curve. And then what you would do next is, you can maybe even make this bold or something. Some people like to decorate it, but whatever. You would then say you're integrating from 0 to 1. You're now writing everything in terms of t. And this is a vector field. So technically, this is a function of x, y, and z. But now you just replace them by the functions that you're substituting in. And then you multiply it by the tangent vector. You multiply it by, maybe we call it t prime at t dt. So the idea is that at every point, as you move across it, there's this tangent vector t at that point. So you evaluate the vector field at the point, and then you take a dot product. This is a vector, and you take a dot product with the tangent vector. And the tangent vector, the way you get it is you just differentiate these components. So then you end up getting that this is the integral from 0 to 1, f of x of t, y of t, z of t, and then you take the dot product with the tangent vector, where you differentiate each of these components. and then you integrate. Now everything is written in terms of t. It's a function of a single variable, and then you just compute this integral, and then whatever number you get, that's what you call the line integral. Okay, that's how you do a line integral. And in the vector calculus class, you just do a lot of examples where you kind of see how to do it. How do you do a surface integral? So now the next question is how to compute a surface integral. So you want to do this kind of an integral. This is S. So as before, we're going to assume, right? We're going to assume that S is a simple surface. And that just means you just need. So again, people in physics, they do not distinguish between mappings and a set. They treat them as the same thing. We do not do that. We are more careful. We always say that you can only integrate over a mapping, even though we often visualize the mapping as the image. So that means you only need one parametrization. So like, for instance, here's like S. This is your curvilinear piece, and you're just mapping the square, right? 0, 1 cross 0, 1. You're just mapping this into S. So here you can call, this is now a function of two variables, so you can call these variables like S and T. Realize not the best notation, maybe we should just call them U and V, let's say. So that's your surface, and you are using, it's a simple surface, you can describe it as a simple parametrization. If it's like a more complicated surface, like if you're integrating, let's say, over a torus, what you would do is you would like decompose it into a lot of pieces. So you're basically writing it as a sum of chains, right? You kind of decompose it, and then you would do then you would sum up, right? You would just integrate over each of the pieces linearly, like all of the pieces individually. So you just have to describe how you do it over a simple surface. This is what we call a chain, a simple chain, basically. And the way you do it is, it's very similar to what you do before. You're going to have an integral. This is going to be an integral from 0 to 1. This is an iterated integral because you're going to bring everything back to the unit square. And maybe this is starting to feel a little bit reminiscent of what we're doing with differential forms. You kind of substitute things back. And then what you do next is, this is your vector field. You have x, y, z, but you're going to replace x, y, z by the functions. This is a mapping. So the x, y, z coordinates are now determined by mappings of, you have 3 separate mappings. So you just substitute in whatever those mappings are. So this would be x of uv, y of uv, z of uv, like this. So now you have a function completely in terms of u and v, but this is not a scalar. This is not a scalar function. So what you do next is you take the dot product, but now it's going to be n, where n is the normal. That's the normal that you get. So the way you get the normal, so that's the normal that's perpendicular to your surface. Now, how do you find the normal? The way you get the normal is by using partial derivatives. So if you flow horizontally like this, maybe I should use a different color. So if you have a point and you flow horizontally, you get a curve like this. And if you flow vertically, you get a curve like that. So you can see that these two curves are intersecting each other and they're tangent to your surface. So to get the two vectors, you're going to partially differentiate. So what you do is, let's say the name of this function that you're using, the name of this mapping is g. That's the name of the function, the parametrization function. So what you would do is you would take dg and you would differentiate it with respect to u. So all that would mean is this function has 3 components, and you partially differentiate each of the 3 component functions. Then you take the cross product with the other derivative. So by taking the cross product, you're constructing a normal, and this is now a vector, and you take the dot product with that vector, and that's the way you do it. It's a tedious computation, but in the end, it does make sense, right? You're computing the normal, and then when you do this, that will calculate for you the surface integral. If you want to, you can also put some decorations in the end. You can write like du, dv, or something. Not that it really does anything at this point, but it just indicates that everything has been written in terms of u and v, and this is just a regular integral of a function of 2 variables, u and v. So that's the way you do a surface integral. That's how you do it. It's fairly tedious to do because you have to first parametrize, you have to substitute, you have to take the cross product, then you have to take the dot product, and then you have to do an integration. The whole procedure is quite involved. Like the whole calculation is fairly long, but that's the way you would do it. So that's the way one does a surface integral. And now let's say what Stokes' theorem says. So this is classical Stokes' theorem. So classical Stokes theorem, this is what it says. It says let F from U to R3 be a smooth vector field. It does not actually have to be smooth. It just has to be continuously differentiable. That means the derivatives, the partials exist and they form continuous functions. But let's just say it's a smooth vector field on U, where U is an open set in R3. Let S be a surface in U. So using our terminology, we would say it's a two-chain in U. That's the way that we would say it. But people in physics will say this is a surface in U. So then, if you were to do the surface integral over S, and it's the curl of the vector field, then that is equal to the integral over the boundary of the surface of the vector field. So what's curl? I do not want to describe what curl is. I'll write it down here, that curl of F is another vector field. So it's an operation on vector fields. If you have a vector field, there's a computation you can do in it called the curl. If you've seen this before, maybe you've seen this, that the curl of F is the cross product between the del operator and F. Maybe you've seen that before. But this is supposed to represent the circulation of a vector field. If this is like a fluid, then around any point you can talk about how it rotates. So there's this operation called curl on a vector field. In physics book, they actually derive for you where it comes from. In a math book, like in a calculus book, they sort of just hand it over to you as a given operation and you just use it. But in the physics book, they might actually show you carefully the motivation for how you derive it. The basic idea is, maybe just to give you, if you have a point, you can draw, let's say, a small little box around the point like this. Well, actually, what you can do is that if you have a point like this, you have three different vectors. You have the vector that points in the I direction, the vector that points in the J direction, the vector that points in the K direction. And then the idea is, if you want to calculate the curl in the I direction, you draw a circle, a small circle around that point that's perpendicular to I. If you want to get the curl in the J direction, you draw like a little circle centered at the point that points in the J direction. And then if you want to do it around K, you kind of draw one that's perpendicular to K. So that's why it's a vector, because it's for each of the three components that you have. And then you consider what happens as you shrink the circle down to 0. And you get like the circulation, like how strong is the current that goes around every one of the circles. That's why it's a vector, because you have three different directions. So it's just a calculation called curl. So if you do curl of F and then you do the surface integral, that's the same thing as doing the boundary of the surface of F. So the idea here would be that if this piece represents a curvilinear surface, and that's the normal. So when you parametrize the surface, this is the normal that you get. The boundary, that's the boundary that you go around it. So this right here would be the boundary. And the way you find the orientation on the boundary is by using the right-hand rule. So you make your thumb point in the direction of the normal, and then if you use the right-hand rule, this is the way you flow along the boundary, right? And what classical Stokes theorem says is that if this is a surface and you calculate the curl of that surface, you do the surface integral, that will give you the same thing if you were to calculate the vector field without the curl along the boundary of the surface where the orientation is taken by the right-hand rule. So how is this related to what we're doing? So here's how it's related. It's actually quite simple once someone shows you what the connection is, and then you just have to do the calculation to check. So the idea here is this. So our vector field, so you're going to write the vector field. So you have three component functions. And now you're going to set omega to be equal to the differential form that you get for each of the three components. So f1 dx plus f2 dy plus f3 dz. Then, this is modern Stokes, will tell us that if we integrate over S, so here we're thinking of S as a two-chain, right? This is just a two-chain. So if you integrate over S, now in mathematical notation, you just write a single integration. So if you integrate over S of d omega, that is the exact same thing as integrating over omega of the boundary of S. Okay? And you have to check, and this is not difficult, you have to check that this and this are the same. So you have to calculate what this is, you have to calculate what that is, and show they give you the same thing. Actually, this is somewhat easy to see because in general, so maybe I'll do that. I'm going to do this one for you, and then you can do the other one. So it's actually very easy to see. So what I'm saying is that if you integrate over, let's say, any curve, it does not have to even be the boundary, but any curve of a vector field, how do you do it? You parametrize your curve, and then you substitute in the parametrizations, and then you multiply it by the tangent vector, and then you integrate this, dt or whatever you want to put at the end. But when you do the integral of the form, how do you integrate over a form? Well, it's you pull it back. You pull back the form. This is a one form, so you pull it back. So when you pull it back in terms of t. So the integral will be in terms from 0 to 1. But then each of the component functions, f1, right? This would be f1 at x of t, y of t, z of t. And then you multiply it by dt. So that would mean that this component function gets differentiated. So you end up getting x prime of t, right? Then you do plus f2, x of t, y of t, z of t. And then you do times y prime of t, and so on. But if you look at this, that's exactly what we have here. We have a vector field with these three components, f1, f2, and f3, and we're taking the dot product. We're taking the dot product with these components, x prime of t, y prime of t, and so on. So it's easy to see that this is the same thing as this. So there's nothing special that you're integrating over the boundary. It's just the fact that if you integrate over any curve, any one chain, calculating the line integral the vector calculus way will lead to the same thing as integrating the form, where the form just represents this, over the curve. So they both lead to the same thing. And then you have to check, that the curl, that this one and this one are also equal to each other. So this is just a computation. It's the same computation that I just did, except it's just a bit more tedious. Basically, what you would do is you will use the formula for the curl. Then you will take the parametrization function for S. You will calculate the cross product. You will put it in, and you get this long, messy computation. And then you will see that's the same thing if you were to take omega, calculate d omega. So you're going to have to calculate the exterior derivative of omega. So this will become a 2 form. So you do that, and then you would pull back the 2 form and do the calculation. And you will see that it coincides, and it gives you the same thing. It's actually very easy to check. It's just a tedious computation with all of the algebra that you have to do. But they give you the same thing. And so what you see here is that when you write everything in the language of differential forms, basically you replace the vector field that you have rather by this differential form, then you can rewrite classical Stokes theorem in the notation of differential forms, and then it becomes a special case of modern Stokes theorem. Before we prove Stokes theorem, we should make just a few more comments. So even more comments. I want to start with that Stokes theorem is also called the fundamental theorem of calculus. The reason for this is because if you write out Stokes theorem, it says that we have this relationship. And when you write it in words, what you're saying is the integral of a derivative is equal to the integral over the boundary. That's what it says. And some people call this the fundamental theorem of calculus. if you look at the classical fundamental theorem of calculus that you first learned, it would say that if you integrate on an interval, so let's say for simplicity our interval is from 0 to 1, but it could be any closed interval, and we're integrating a derivative, then that would be equal to f of 1 minus f of 0. But what is this? This is really the integral of the function without the derivative, so it's just the integral of f. But what's the boundary here? Well, the boundary here are just the endpoints. So the interval from 0 to 1, this is its orientation. So this one is taken to be positive, and this one is taken to be negative. So you're integrating the boundary of the interval. But here, you're integrating the boundary, but the boundary consists of just 2 points, and integration is a sum. So you're summing the function over its boundary. So you're summing it at 1, so you get f of 1, and then you're summing it at 0, and you're getting f of 0, but it's taken with a negative sign because that's the orientation that you get. You're calculating the boundary of that interval. And so this is why we call it the fundamental theorem of calculus. Now, the other thing I wanted to mention is, so as we've said before, there are 2 versions of Stokes' theorem. There's one for chains, and there's one for manifolds. So the one for chains, we just written out that if you have a manifold and you have a differential form on the manifold, then if you were to integrate the exterior derivative of your form over a chain, then that's the same thing as integrating the form over the boundary of the chain. Okay. Now, the version for manifolds is a little bit different. So this is the other version. So here's what it says. It will say that suppose X is an oriented. So here it has to be oriented. If the manifold is not oriented, then the integral is not going to be defined. This is a different type of integration. Suppose X is an oriented n-dimensional manifold with boundary. It's something that we did not define before, but intuitively we understand what that means. So it's an n-dimensional oriented manifold with boundary, and let's assume that it's also compact. It does not have to be compact, but compactness just assures us that there's no issues of convergence and things are finite. And now we're going to have a form. And let omega be an n-1 form on X. Okay, so then if you were to integrate d omega over the manifold, so it's a different type of integration. It's no longer an integral of the chain, it's over the manifold. Then that is the same thing as integrating omega over the boundary of the manifold, where this is, so this is something we've never defined before because we just do not need to know that, but this is called the boundary of X. It's the boundary of the manifold, and it inherits an orientation from the original manifold. It also happens to be compact. If X is compact, then its boundary is compact, and it is oriented because it gets an orientation from X. This is something that we're not explaining how to do it because we do not need it for the purposes of this class, but I'm just bringing it up so that you are aware that something like this exists. If you want to see details, you can of course read the Breton book on that. This is a more complicated theorem. So what this would say is, for example, X can be the cylinder, including its boundary. That would be X. X is the cylinder. And then you give it an orientation on the cylinder. So you can orient the cylinder so that the normal points outwards. And basically what that means is all of your charts, when you map the charts to X, you make sure that decide points outward. So since you can do that consistently, you can come up with an orientation on x. It does not matter how you orient x. All that matters is that an orientation exists. Recall what we said. There's no such thing as a positive orientation or a negative orientation. We just talk about whether or not an orientation exists. So you orient x. Let's say that's the way you orient x. And then the boundary of x, well, you can see what that would be. That would be the two rings, the two disjoint circles that go like this. And the orientation that you put on these circles, it comes from the right-hand rule. So if you want to see how it works, just imagine you have a small little curvilinear square over here whose orientation points outwards. And then if you use the right-hand rule, you will see that the boundary goes like this, right? So this one will be oriented like that, and the one below will be oriented in the other direction. So the way you see it is just draw a small little curvilinear square, and then use the right-hand rule where the thumb points in the direction of the orientation that you've chosen. And then if you use your right hand, you will see that you're getting something that goes like this. So then that would mean, again, this is intuitive, this is not formal or anything, but this is just the idea that the boundary of x will be a manifold that is the union of these two circles, two disjoint circles, and the orientation that you're going to put on these circles, it's inherited from the orientation that you're putting on x itself. And that's the way you would orient them, and this is what the theorem says. So this is the other version of Stokes' theorem. Okay, so these are just some preliminaries. Well, I should not call these preliminaries. These are just some comments that I wanted to say before we finish. And maybe I should just say one last thing. This is just the last thing. So if x is compact and oriented manifold, notice I'm not saying manifold with a boundary, but just manifold, then if you were to integrate over x d omega, then that would be 0. Well, you could say that by Stokes' theorem, this is what you can say. You can say by Stokes' theorem, it should be omega of the boundary of x. But there is no boundary because it's just a manifold. Like, for instance, if you take a torus, what's the boundary on the torus? There's no boundary. If you had something like this, then the boundary would be all of that. But here, there's no boundary. But maybe you're bothered by this fact because you might say, well, that's the statement of it, it's sort of pathological in a way because this is empty. Is there another way to justify why it's 0? So if that bothers you, what you can do is, so if let's say you have, so let's say this was your manifold. Let's say this was x. Then here's what you can do. You can cut x, let's say, into two pieces. Call this x1, you call that x2. And then you would say that the integral over x d omega would be the integral over x1 d omega plus the integral of x2 d omega. Now, you might be bothered by this statement. Again, we're being kind of sloppy here because we've not really carefully defined integration on manifolds. We're only talking about integration on chains, but it does kind of make sense. You sort of split it into two pieces, and these are two manifolds, and this is their common boundary. And then by Stokes' theorem, this would be the integral of omega, the boundary of x1 plus the integral of omega, boundary of x2. But the boundary of x1, that one will be oriented, let's say, one way, and the boundary of x2, it will actually be oriented the other way. And then these end up canceling out. So you're integrating over the same thing. Their boundaries are the same thing, but they cancel each other away, and you end up with 0. So that's just a nice thing to know, that if you have a compact oriented manifold and you integrate a differential of a form, that you always end up getting 0. And the justification for that is Stokes' theorem, a little bit suspicious of a proof. I understand it's too pictorial. Like, what is x? How do you rigorously define x1 and x2? How do you rigorously justify that this sum is equal to that? Of course, it requires further justification, but I just want to bring it up here because it nicely connects with the lecture. Fortunately, we will not need to know this because we just need to know integration on chains, but I figured it would be appropriate to bring this up. But now we're going to get to the proof of Stokes' theorem. Now we get to the proof the proof of Stokes' theorem, which I'm very glad that we're actually doing this, because when I was in graduate school and I've seen Stokes' theorem, it was just asserted out of nowhere. No one ever proved it. So I made it a statement to myself that if I ever teach a class, I will make sure that it gets proven properly, so that you leave the semester with the understanding of how to prove it. Now, I should say a warning here. The proof is very long. However, and this is the amazing part, it is very straightforward. There will be absolutely no cleverness in this proof whatsoever. There will be no trick out of anywhere that makes this work. The proof is difficult, not just because it's long, but because there's so many definitions that you have to recall properly, and you have to be comfortable with them. But fortunately, this proof is recorded in video format, so you will be able to pause it, go back, rewatch it, think it over until it makes sense to you. And as you know, I like to over-explain things. I like to drag things out, making sure that the details are not overlooked. So I have no idea how long this is going to go on for. Hopefully, we can do it in like 45 minutes. If you're not interested in the proof, if you just want to accept it, you can just accept it. But for the sake of completeness, we're going to write out the proof. So first, it's a good idea to begin with the statement of the theorem. And the theorem says that let X be a manifold. Does not matter what dimension it has, be a manifold. And it does not need to be oriented, and it does not need to be compact. Because when you're integrating over chains, they're automatically oriented because they're chains, right? They're coming from cubes, right? So they're automatically oriented, and they're automatically compact, right? Because the cubes are compact. I mean, technically, chains are not compact, right? Because they're mappings, they're not they're not spaces. But I'm of course referring to the image of the chain. So let X be a manifold, and C is a chain of dimension n. So that's a chain. And here by chains, we of course mean we're defining chains using cubes instead of simplices. So we have a chain, and omega is a form of degree n-1. Okay? So then we have this beautiful relationship that if you integrate d omega over c, notice d omega, that becomes 1 degree higher. That is the same thing as integrating the boundary of the chain of omega. So now we're going to write the proof. And the proof will consist of several steps that will keep on simplifying the equation. Now, when I say the equation, I'm referring, of course, to this. This is the equation that we want to prove. So we will keep on simplifying that equation into something we can compute. We can compute more easily. So the first simplification, this you can say is the first way you can simplify this. We can assume that C is a simple n-chain in X. What does it mean to be a simple n-chain? Well, recall the definition of an n-chain is a formal sum of mappings. So a simple n-chain is when you just have one. So in other words, C is equal to sigma, where sigma is just a single mapping from the n cube into your manifold X. This is a smooth mapping, by the way. This is a smooth mapping. What does it mean to be a smooth mapping on the n-dimensional cube? It just means that sigma can be extended into an open set containing this cube, and then it's just smooth in the manifold sense, as we've talked about. But we often just write it like that. It's just easier not to introduce extra notation unless we really have to. Okay, now, so we can assume, now why are we allowed to assume this? So we can assume this by linearity. Maybe I should add this in by linearity of integration. So the way we integrate over a chain, by definition, is we sum up all of the pieces. We integrate over the components, the pieces that make up the chain, and we just sum them up. That's the way we define it. How do we calculate the boundary operator of the chain? Well, you do it by linearity. You distribute the boundary operator on each piece, and then you sum them up. So this allows you to automatically assume that you have a simple n-chain. Okay, that's the first simplifying assumption. The second simplifying assumption would be we can assume that our chain from in into x is contained. Now I'm being a little bit sloppy over here, but when I say is contained, I'm referring to the image. That's the way we visualize the chain as the image set in our manifold is contained in a single chart. So i.e., there's a single chart. So now what's the dimension of this manifold? We do not really care. Let's call the dimension of the manifold m because we're already using n. So there is a mapping phi. Now I'm not going to call it phi lambda because I'm choosing a particular index, right? I'm choosing a particular chart. So let's just call it phi. So there's a map phi. A manifold is locally Euclidean, so it's a Euclidean space of, let's say, dimension m. So there's a homeomorphism onto an open subset of x with sigma of in, right? That's the image of the chart being contained in the image. I'm sorry, that's the image of the cube being contained in the image of the chart. So we can assume this. Now, why are we allowed to assume this? So I'm not going to write out a proof here explaining why we're allowed to assume this. But I'm going to give you a fairly convincing argument because I do not, this proof is long as it is, and I do not want to make it longer. I just want to give you the main ideas of why it works, like the big idea of why it works. But basically, just imagine for a moment that if you had, let's say, a two-dimensional cube, and you map it into x, and this is like the image that you get, but the image is not contained in a single chart, you have to partition it. So let's say you partition it into smaller pieces like this. And now each of the pieces are sitting inside a chart, right? So you've partitioned it so that the pieces are sitting inside the chart. You're going to, so you're going to prove, so by proving it in step 2, we're assuming that the images of all of these 4 sub-cubes, Stokes' theorem is true on all of them. So it's true on this one, it's true on this, so it's true on all of them. Now notice what happens when you sum them up. If you look at the boundary around this one, and so if you look at the boundary, so maybe it would be better to do it like this. If you have 2 of them coming together, and you look at the boundary for this one, like that, and then you look for the boundary for the one that's adjacent next to it, notice what's happening, that the cubes that share a common boundary, this one goes the other way, sorry about that, that one goes down. So I completely messed this up. So this should go like this, like that, yeah. So notice that cubes that are adjacent, that share that common edge, that will be canceled away in the boundary, when you calculate out the boundary operator. And so by partitioning your square small enough so that each of these sub-cubes are now contained in the chart, when you calculate the boundary operator, you're just going to be left with the outside piece anyway. And that means that you can reduce the proof of Stokes' theorem to the special case where every one of the cubes is contained in a single chart. Now, of course, that's the basic idea of this, and you have to write out the proof, but I think that's pretty believable. Like, you can kind of see why this is beginning to work. And then I really want to get to like the main idea, and that basically means to actually do this calculation, do that calculation, and you see why they come out to be the same thing. I would say that part 2 is less topology and more analysis. Okay, so we have part 2. So what do we do next? Well, with this assumption, let's think about what we're trying to prove. So we need to show that if you integrate C, so in this case, C is sigma d omega, that's equal to the boundary of this one. In this case, this would be d sigma of omega, right? Now, how do we calculate a integral? How do we calculate these integrals? So here is what we'll do. I'll draw a picture for you. So this is our manifold. This is our cube. Okay, this is our manifold. This is our cube. And this is our chart, Rm. So the way we calculate this, now omega is, by definition, it's a collection of Euclidean charts, right? That's what it's a coherent collection of Euclidean charts. So you just find the corresponding way omega is represented in this chart. Now, because I'm suppressing lambda, I do not want to use extra letters. I'm just suppressing lambda. It's for some lambda, so let's just call it phi. There is some differential form, Euclidean differential form, that we're going to be integrating over, that we're going to be pulling back. And let's call it, instead of calling it omega lambda, let's just call it omega again, right? I know it's sort of conflicting with that notation, but let's just call it omega again. So we have omega right over here. And what do we therefore do? In order to integrate this, so we have to pull back the form back to this cube. So we have this a composite function over here. Let's call it G. I'm going to call it G. So where G is sigma composed phi inverse. Right? You go like this, and then you can go back because the image is contained, because the image of sigma is contained in the image of phi. So when you do this composition, it is going to be defined on all of In. So you have this mapping, and you have omega. And this is a form. Omega is an n-1 form, and you're going to pull it back. So you can pull it back over here. Okay. So now, by definition of integration of forms, right? This is the definition of integration of forms. This is the previous lecture. This is the way we integrate. If I want to integrate d omega over sigma, I represent sigma. I put sigma in the correct, well, I put sigma into a chart that contains it. So here's a chart that contains it. And omega is represented by a Euclidean form. And then this composite map that you have, this composition, you pull it back. So you can pull it back here, and that would be G upper star omega. Okay, that's what that would be. So you pull it back to In. And so how do you calculate the left-hand side? The way you calculate the left-hand side, this would be the integral of, so the integral of sigma d omega is equal to, by definition, you will pull it back, right? You just take this thing, you pull it all the way back to the cube, to In. And then, right, you do G star applied to d omega. So at the moment, we're doing it for d omega. So I guess I should have said that, I mean, in general, that's how you integrate a form. But in this case, I mean, it's true, you have omega defined on Rm, but technically you're integrating d omega. So you take this omega, you calculate its exterior derivative, you now have a form on this Euclidean space, and then you use G to pull it back, and you're getting a differential n form on In. Okay, and whatever this is an n form. An n form on In. So notice the degree of the form matches the dimension of the cube. So that means you're using all differential symbols. So in the end, you're just going to have that whatever this is just going to be some function, some smooth function, and then you will have all of the differential symbols at the end, right? You'll have dx1 wedge dxn. I mean, it has to be, because it's an n form on the n cube. So that means you have to use all n coordinates. So whatever coordinates, so by coordinates, I just mean the projection function. So whatever letters you use to represent your projection functions, so let's say we're calling them from x1 to xn, then when you pull it back, you will have to use all of them, and it'll just be some coefficient function, and you're just integrating that coefficient function. This is a function of n variables, and then you just do the regular integration of a function of n variables. That's the idea of what it is. So that's the way that you do it. Okay, now, one thing that you can do here that might be helpful is, I'm going to rewrite this just a little bit. So you can say that the integral of g star of d omega can also be written as d of g star of omega. This was a question on the homework. So the question on the homework is that pullback commutes with the exterior derivative operation. So we can just rewrite it like this. So basically what we can do is, instead of taking the exterior derivative of omega and then pulling it back, we can rather pull back omega first and then take the exterior derivative of that afterwards. That's basically the chain rule. I mean, the reason for why that works, that's basically the multivariable chain rule. Okay, so you kind of, but it's the same idea, right? This is an n-1 form on the n cube, and when you take its exterior derivative, you now have an n form on an n cube, so in the end, it's going to look exactly like this. And then you calculate whatever that is. So this is the left-hand side. Okay, so let's write it right over here. We can say that that integral can be replaced. We can say that this can be replaced by an integral of in d g star omega. Okay, that's what we have. And now we have to do the same thing with this one. The same thing. So this is what I mean over-explain. If you're reading it in a book, they might just jump directly from this to this, leaving everyone confused. But this is like very carefully explain what we're doing. And now we're going to do the same thing with this one. So I'm going to remove this, because this is really what we're after. We're just rewriting it in a different way. And as you can see, everything we're doing right now, there's no clever ad hoc tricks at all. But it's still difficult because the definitions are difficult. Okay, so now we get to this calculation. This one is trickier because you have this boundary operator. Okay, now the boundary of sigma is equal to, and this is by definition of the boundary operator on cubes. This would be a sum of, so this is an oriented sum, and we write it like this: partial I comma j of sigma, where I ranges from 1 to n, and j ranges between 0 and 1. Now, let me just remind you again what this is. So without math symbols, it just means substitute j. So substitute 0 or 1 into the ith coordinate of sigma. So that's what that means. So sigma, it's a function of n variables. The I represents which of the coordinates you're choosing. So you choose a coordinate from 1 to n. And then you're going to choose either the front face or the back face of the cube. So that's why j is either 0 or 1, right? Front or back. That's what you're doing. Now, maybe to make the notation a little bit easier, it would be helpful. It would be helpful to introduce an evaluation function. So let's call this function epsilon for evaluation, and we're going to evaluate at I comma j. So this is going to be a mapping from the n minus 1 cube into the n cube. So keep in mind that each of these faces of the cube is of one smaller dimension. And this evaluation function, here's what it does, where if you take epsilon I comma j of an n minus 1 tuple. So let's say the n minus 1 tuple, the coordinates are denoted by y's, from y1 to yn minus 1. And the way you map it into in is you're going to just copy and paste everything. You're going to keep everything the same. But in the ith coordinate, right, you can see the first I minus 1 coordinates are exactly the same. Nothing changes. And then the ith coordinate, you're going to set it equal to either 0 or 1. So you're going to set this j. Now, when you write j, this is of course 0 or 1, depending on what you set j to be, because j can only have 2 choices. And then after that, you just repeat everything exactly the way it is from before. So you have this evaluation function. So if it makes you feel better, you can say, so this boundary is nothing more than sigma composed with this evaluation function. That's another way you can put it. And by doing this composition, you now have a cube. You have a mapping of a cube of one smaller dimension. And that's how you get the faces of the cube. Okay, so we have this. Now, we want to calculate the right-hand side. So let's carefully write out what the right-hand side is. So thus, if we do the integral of omega of the boundary of C, that would be equal to, now we have to understand that the boundary of C is a four sum of all of these chains of one smaller dimension. And since integration is linear on chains, this would just be a sum where I will range from 1 to n, and j will range from 0 to 1. Then you have this alternating factor, and then you will integrate, omega over each, not of sigma, but of the boundary of sigma. So then you will integrate omega over the I comma j face of sigma, like that. Okay, so, and now we're going to rewrite this a little bit. So how do you compute this? Well, the way you end up computing this is actually very similar to what we have in this diagram. So in this diagram, we're rather going to map the n minus 1 cube into x, and this is boundary I j sigma, right? Because this face is now a mapping on a cube of one smaller dimension. Then we have Rm going into phi, because these chains, they're still contained in the same chart, right? Sigma itself is contained in the chart. So the boundary of sigma is still contained, because the boundary is included, of course, in sigma. So the boundary is still contained in the same chart. So we're still using the same chart. And we're going to take this sigma, and we're going to pull it back. So we have this composition function. So let's call this composition function gi comma j. Okay, let's call this composition function, because you're getting a composition function for every I and j. You're doing this for every I and j. So you're going to pull it back using this one. So we would therefore say that this is equal to the sum. I'll just write I comma j minus 1 I plus j. And then here, you would write this is the integral of, now what are you doing over here? What you're doing over here is you're going to take this omega, you're going to pull it back to the n minus 1 cube using this mapping. So you're going to take omega, and you're going to pull it back using this mapping, and you're going to integrate over n minus 1. Okay, that's what you're going to do. You're going to integrate it over the n minus 1 cube. This is an n minus 1 form, right? Keep in mind, omega is an n minus 1 form. I do not want to scroll back up, but this is an n minus 1 form in the statement of the theorem. So when you pull it back, you have an n minus 1 form, and so you basically just have a smooth function followed by all of the differentials. So you're just going to be integrating this as like a usual integral on an n minus 1 cube. So this is what you have to compute. Now, this piece, it would be helpful to rewrite this using the evaluation functions. Because, I mean, what is this, right? So behold, right, so observe that we have the following diagram. We have I n minus 1 going into in. This is epsilon I comma j. That's the evaluation function. And then in. So we have in goes into Rm using G. This is the map that we have over here from before, right? That's the map that we have over here from before. And then we have this new mapping from in minus 1 into Rm into the same chart. This is what we're calling Gij. So it's convenient to realize that this, and we have a form over here, right? We have a form that we're pulling back. So when you pull back this form using this mapping, that's the same thing as, because this diagram commutes, that's the same thing as pulling it back using G and then pulling it back like this. So we can therefore rewrite this and say this is the sum I comma j, I plus j. This is going to be the integral of I n minus 1. And now you're going to use the fact that you're just using the fact over here that if you have omega and you pull it back like this, because pullback is sort of like a contravariant functor, pulling back omega this way is the same thing as pulling it back like that first. So you would write, and then you pull it back one more time using these evaluation maps like that. And then when you integrate that, so maybe just to over-explain this, omega is an n minus 1 form. You can pull it back using G, and then you have an n minus form on the n cube, but then you take that n minus 1 form and you pull it back one more time, and then you have an n minus 1 form on the n minus 1 cube. So this is what you end up with. Okay, so this is what we're ending up with. So what are we trying to show? So we have rewritten, so I think I should probably scroll out so it's a bit easier to see. I still have to scroll out. You can see pretty long proof, but here is we have taken, so okay, we're trying to justify this. So this is the main fundamental equation that we're trying to prove. And we have taken the left-hand side and we have rewritten it in this way. Okay, so I'm going to rewrite it right over here. So the goal is to show that, so the left-hand side can be rewritten like this. This is the integral of in d of g star of omega. And it's the same thing as this, right? The right-hand side, we have manipulated it. It was equal to that, that was equal to this, that can be rewritten using evaluation functions. So this is equal to the sum. And we have the integral I n minus 1 epsilon I comma j star g star omega. Now, what is g star omega? G star omega, so omega is some form, and when you pull it back, g star omega, that is an n minus 1 form on the n cube. So whatever this is an n minus 1 form on the n-dimensional cube. Okay, that's what that is. So it's the same, it's the same thing. So we have managed to reduce the proof of Stokes' theorem to the following special case. So all of this stuff, we can forget about it. And let's say what we managed to reduce everything to. So this, you can say, is step 3. This is called reduction to the standard cube, to the standard n-dimensional cube. Basically, is to show this. So if, now, what you will notice is there's nothing special about this. This is something. This is some kind of form. So you can give it a name. Just give it a new name. Let's call it zeta or something. It's a new form. Whatever it is, it's just some kind of n minus 1 form. So if zeta is an n minus 1 form on the n-dimensional cube. And by the way, whenever we talk about something being an n minus 1 form on the n-dimensional cube, what we really mean to say is zeta is an n minus 1 form on an open set that happens to contain the n cube. But we just do not bother to say that because that's too wordy to write that out. But you always kind of keep that in mind. So omega is an n minus 1 form on the n cube. So then, this is what we have. We have shown that if you integrate over in d zeta, right? So if you take this n minus 1 cube, you calculate its exterior derivative, and then you integrate that. By the way, integrating that means that's just the usual integral, because this is an n minus 1 cube. When you take its exterior derivative, you get all of the differentials. So then you get a function followed by the differentials, and then you just integrate the function in the usual sense. That if you were to integrate that, that will give you the same thing as where I goes from 1 to n, j goes from 0 to 1, minus 1 to the I plus j, and then this would be the integral over the n minus 1 cube, and here we're do the pullback, we do epsilon ij applied to zeta, where epsilon ij is the mapping from the n minus 1 cube to the n cube. And how is this mapping defined? Well, here it's convenient to introduce different letters to distinguish between coordinates. So maybe we call these y1 up to yn minus 1, and we call these coordinates x1 up to xn. And then what we're saying is epsilon I comma j takes these coordinates and it assigns them, it keeps them in the same order. So you get to y minus 1, you kind of keep it the same, and in the ith position, you set it equal to j, and then you just keep the rest of the coordinates exactly the same way. So why do we call this reduction to the standard cube? Because the idea here is you get rid of the manifold and only work with cubes. That's the idea. That the original statement had to do with manifolds. It had to do with mappings of the cube into the manifolds. And by doing these simplifications, you're able to bring everything back to the cube. So basically, in some sense, you're proving it in the easiest possible case, where you just have a standard plane cube that's not curved or anything, and then you're showing that if you integrate over the cube, that's the same thing as just integrating over the sides of the cube with the proper orientations and then summing them up. That's basically what you're saying, right? That's why I call this reduction to the standard cube. So we started, you see, this is the way the proof begins. The proof begins on the manifold, right, and all of that. But then these simplifications along the way, when you kind of go through this process very carefully, you no longer have to do anything with a manifold. there's no manifold anymore, right? This is just cubes, right? That's just cubes, and this is just regular integral, and this is going to be a regular integral because when you pull n-1 form, you're going to have an n-1 form on an n-1 cube, and then this is just going to be a regular integral that you're going to evaluate. So the next step is to actually go through this, and this is what I think is the most interesting part, to do this calculation carefully so you get to see it. Okay, so if you manage to get up to this stage without getting lost, then congratulations. And now we get to the next part where we actually have to do the calculation and compute the left-hand side and compute the right-hand side and see that they actually give you the same thing. I think this is the most interesting part of the proof. Now, I just realized that this is an unbelievably long lecture. So instead, what I'm going to do is we're going to put this as a homework problem with hints and steps. So you'll be able to do it yourself. This is actually not hard. It's a very pleasant computation. It's a very nice computation. It just looks intimidating, right? But when you work it out, you're going to see it's not bad whatsoever. And if you want to get a reference to this, you can look at Spivak, Calculus on Manifolds. And let me just give you the part of the book, so give me a moment to look that up. So you can find this on page, this is page 102, and there is no like first, second edition or anything. There's just one version of the book. So it's page 102, and the name of that section is called Fundamental Theorem of Calculus. That's what it's called. So if you look at page 102, he has Stokes' theorem, and he starts proving it. His notation might be a little bit different, but ultimately, he's going to be doing exactly what we're doing. So if you want a reference to look it up. And I also recommend to look at page 104, where he has that quote that I mentioned, where he says, the theorem is trivial. It is trivial because everything has been properly defined. And despite being trivial, it has important consequences. So I think with that, we will finish. And then you'll do that pleasant computation, the most exciting part of the proof, on the homework yourself.